In the late 1800s, scientists were making amazing breakthroughs in all fields of science. Determined, scientists began to look to the field of physics and soon discovered radiation. Scientists found that if they removed the air from a tube and shot electric currents through the remaining gas, a beam would be produced from the cathode to the anode. When the paddle wheel was inserted, the wheel would turn. This meant that cathode rays behaved like particles. In 1897, Sir J. Thomson identified these negatively charged particles as electrons. In 1895, experiments with cathode rays conducted by Wilhelm Röntgen investigated the secondary emissions caused by cathode rays. He covered a cathode ray with black paper and allowed the ray to strike a metal plate. The rays outside the cathode tubes caused fluorescent materials to glow when exposed to photographic film. He called these X-rays. Realizing that they could penetrate some materials, like skin, but not others, like bone, Röntgen took the first X-ray of his wife's hand. Henry Becquerel was experimenting with fluorescent minerals that included uranium. He noticed that when uranium was left on photographic paper, it would leave a bright glowing mark. He assumed that this was caused by the sun. One night, Becquerel stored some uranium in a drawer with some undeveloped film. Although he did not expect to see anything on the film, he decided to develop it anyway. To his surprise, a bright yellow outline of the uranium showed up on the film. It was later discovered that the emissions let off by the uranium were not X-rays, so Becquerel named them Becquerel rays. Later, Pierre and Marie Curie started analyzing uranium. They found that the uranium itself produced emissions. They also found that thorium produced emissions much like it. And the more of these elements in a compound, the stronger the emissions. During their study, the Curies also discovered radium and polonium. This is when Marie coined the term radioactivity. Ernest Rutherford used the newly discovered radioactivity as a means to explore the atom. During this time, the atom was thought to consist of a sea of positive particles with electrons within it. But when he shot positive particles at a piece of gold foil, most of the particles would penetrate the foil and only a small amount would be redirected. This showed that the positive part of an atom was much smaller than previously thought. This is how the current planetary model of an atom came about. In 1932, British physicist James Chadwick discovered the atom nuclei contained neutral particles that he called neutrons. The neutron had no electric charge and is similar to the mass of a proton. Since it is neutral, it was difficult to detect. However, unlike protons and electrons, when the neutron is outside the nucleus, it is not stable. In this planetary model of an atom, the electrons are shown in black, the neutrons are shown in blue, and the protons are shown in red. Near the turn of the 19th century, John Dalton made an atomic theory. This theory stated that all matter is made up of atoms. Atoms are indivisible and indestructible. All atoms of a given element are identical in mass and property. Compounds are formed by a combination of two or more different kinds of atoms, and a chemical reaction is a rearrangement of atoms. Because of the discovery of radioactivity, much of Dalton's atomic theory has been disproved. Two of his laws, one being all matter is made of atoms, atoms are indivisible and indestructible, and all atoms of a given element are identical in mass and properties, have been disproved by radioactivity and the founding of isotopes. An isotope is when several atoms of the same element have different masses because of the amount of neutrons in their nucleus. The discovery of isotopes also led to the discovery of radioactive decay. Radioactive decay occurs when certain isotopes of elements lose some of their particles or energy in order to become stable. There are three different types of radioactive decay: alpha decay, beta decay, and gamma ray decay. Alpha decay is the slowest and least penetrating, and it happens when a radioactive atom emits an alpha particle, which consists of two protons and two neutrons bound together into a particle identical to a helium nucleus. Beta decay occurs when a nucleus emits a beta particle, which is actually an electron. But since there are no electrons in the nucleus of an atom, the electron comes from an unstable neutron particle. Gamma radiation is the fastest and most penetrating. It is when a nucleus of a radioactive atom releases energy. Unlike alpha and beta radiation, gamma radiation is in the form of a wave.
It's a wave!
Radioactive decay was better explained by Albert Einstein in his equation E=mc². This showed exactly how energy was related to mass in relation to isotopes and the speed of light squared. This equation could be used to calculate the amount of energy released in a radioactive reaction or nuclear reaction. Before and during the Second World War, Einstein was involved in something called the Manhattan Project. This was used to see if nuclear reactions could be weaponized. It was found that nuclear reactions could be weaponized, but would leave huge destruction and radioactive pollution. 2 bombs were made during this project. One was a fission-type bomb, which would use uranium in order to split atoms and cause destruction. The other was a fusion-type bomb, which would use a starter of a fission reaction in order to get hydrogen particles moving at fast speeds to merge into one helium particle, causing huge devastation. The bombs were tested, and the United States used them in a counterattack against the Japanese, who were allied with the Nazis and were said to have bombed Pearl Harbor. On August 6, 1945, the United States dropped the first ever fission bomb on Hiroshima. 3 days later, the United States dropped the first ever fusion bomb on Nagasaki. This was the first and only time that atomic bombs were used by any country during warfare. After the war, nuclear reactions were looked to as a means of alternative energy. A nuclear reactor, such as this one at the CANDU facility, uses nuclear reactions to create energy. Elements such as plutonium, radium, and uranium could be used with nuclear fission in order to split the atoms apart and create large amounts of energy. Inside of a nuclear reactor, a neutron is shot at uranium-235, which causes the uranium-235 to turn into uranium-236, which is very unstable and rapidly decays within the reactor. This process is called artificial radioactivity. Many safety precautions had to be taken, such as the use of heavy water as a moderator. The heavy water would slow down the reaction in order for it to occur, but if it was dumped, the reaction would stop. Even though many precautions are taken, devastation can still happen, such as the events of Chernobyl in the Ukraine. When Reactor 4 of the Chernobyl facility in the Ukraine melted down, uranium was released into the environment. The fires and pandemonium caused many deaths, not to mention the deaths from radiation sickness from the uranium seeped into the environment. Because of the Chernobyl accident, the nearby town of Pripyat is now a ghost town, and will be for millennia, because of the amount of radiation in the area. The leftover products of nuclear reactions are a very large problem. They take millennia to decay and cause very serious adverse effects on humans and other living things. Radioactive waste is very hard to store and very poisonous if it gets into local ecosystems. The only way of disposing of radioactive waste is for it to be put into barrels and buried beneath feet of concrete. Radioactive waste is very harmful to the human body. It will not give you superpowers, but instead can cause nausea, vomiting, serious disease including cancer, and in many extreme cases, death.